Hello, my name is Dr. Dan Wedding, and this is DrWedding VB15 Bubble Sorting a One-Dimensional Array. It is very common to sort an array of numbers from high to low and from low to high. This video will cover three variations that are very similar and very easy. The most simple way to sort an array is with an unoptimized bubble sort. This is a brute force method of sorting and uses more computer time than necessary. The advantage is that it's very easy to understand and write. With a few minor changes, the unoptimized bubble sort can be made a lot more efficient and take a lot less computing time. With a few minor changes, the optimized bubble sort version 1 can be made slightly more efficient and take slightly less computing time. Below is the unoptimized bubble sort. It is easier to understand when you analyze it from the inside out. It is also the basis for the other bubble sorting routines in this video. At the center of all sorting routines is a swap. Pretend you have a glass marked milk and a second glass marked orange juice, and someone put orange juice in the milk glass and milk in the orange juice glass. To swap the milk and orange juice, you need a third glass. First, pour the milk glass into the temp glass. Second, pour the orange juice glass into the milk glass. Third, pour the temp glass into the orange juice glass. So the code to swap the drinks is shown below. However, we are sorting an array. By substituting the glasses for variable names, the new code is shown below. You only want to swap the two values in the array if they are out of order. So you can put the swap inside of an if statement as shown below. If you change the greater than to a less than, it will change the sorting routine from low to high into a high to low sort. This if is only looking at the first two values. We need to make it work on the entire array. This is similar to what we did in the previous video. First, put this code in a loop. Second, make the loop index match the array index. Third, verify the array bounds are not exceeded. The largest value added to the array index I is 1. So, you must subtract 1 from the end of the loop. The stopping condition, 19, becomes 18. This routine finds the largest, or the smallest, value and pushes it to the end of the array. It only puts one value into the correct place. Assume you have the 5-element array shown below and you run the code segment shown. When I equals 0, array 0 and array 1 are compared. The if is false. 10 is not larger than 22. So the values are not swapped. When I equals 1, array 1 and array 2 are compared. The if is true. 22 is larger than 9, so the values are swapped. When I equals 2, array 2 and array 3 are compared. The if is false. 22 is not larger than 37, so the values are not swapped. When I equals 3, array 3 and array 4 are compared. The if is true. 37 is larger than 2, so the values are swapped. This code only puts one value in the correct place. It will move the largest or the smallest to the bottom. In this example, the 37 was pushed to the bottom. To sort the entire array, you must run the inner loop for each array element. This is done by dropping the previous code into an outer loop. This is the final code that makes up an unoptimized bubble sort. This sort routine will sort a 20-element array from low to high. This routine will run the if statement max multiplied by max minus 1 times. So, a 10-element array will check the values 10 times 9, or 90 times. A 100-element array will check the values 100 times 99, or 9,900 times. And a 1,000-element array will check the values 1,000 times 999, or 999,000 times. To speed things up, we have to minimize the loops. The outer loop is first. By changing it from a for loop to a do while loop, we can stop when the array is sorted. Note, the variable sorted in this example is a Boolean. This outer loop assumes the array is sorted. If anything gets swapped, it isn't sorted, and the outer loop needs to run again. To speed things up more, we have to minimize the inner loop. Every time you run the inner loop, one more value is in the correct position at the bottom of the array. So we don't need to run to max minus 1 each time. We can reduce the stopping value by 1 at the end of each loop. Assume int stop is an integer in the code below. Because the inner loop is being reduced by 1 after each pass, and the outer loop is waiting for the array to be sorted, there's no way to determine how many times this if will be checked. The last variation is only slightly better. Instead of decreasing int stop by 1 each time, this version keeps track of where the last swap took place and does not go past that array element. In the code below, assume int temp is an integer. The easiest way to demonstrate this is through an example. I have opened up a new project named VB15. I have also generated a form. This form has 4 buttons, 4 text boxes, and 4 labels. The first button, Fill Array, will generate 25 random numbers and store them into 3 different arrays that are all exactly the same. It will then print the unsorted array to the first text box. The unoptimized button will take one of the 3 unsorted arrays and sort it using an unoptimized bubble sort. Then it will print the sorted array to the second text box on the screen. The third button, the optimized V1 button, will take the second unsorted array and sort it using the optimized version 1 sort routine. It will then print the sorted array to the third text box. The optimized V2 button will take the last unsorted array and sort it using the optimized sort version 2, and it will also print the sorted list to the fourth text box. Now let's look at the code. I've typed in the comments at the top of the code and declared some variables. You'll see that there are 3 double arrays, all with 25 elements each. They're indexed 0 through 24. I've minimized the subroutines so we can look at them one at a time. The first one is form load. The only thing form load does is it calls randomize. We're going to be using a pseudo-random number generator to generate our random numbers that we're going to sort. If you don't remember how to use a random number generator, you should go back and review the mathematics video. Because form load only has randomize in it, I'm going to minimize it. The next subroutine is one that I wrote, and its only purpose is to clear off the 4 text boxes and clear 3 of the labels. I created this subroutine so I could eliminate these 7 lines from other subroutines. This subroutine is also going to be minimized. There's no reason to keep it open. The third subroutine will print an array to a text box. These 3 lines would have been in every button press. Therefore, I made them into a subroutine and just called sub_print_array. There's no reason to keep this subroutine open. The fourth subroutine just swaps 2 values. I did not want these 3 lines in the center of every one of my sorting routines, so I turned it into a single subroutine called swap. You'll notice that I used milk and juice like I did in the PowerPoint examples. The 4 button codes are the code that I really want to focus in on. Let's look at the first button. The first button will reset the form. ResetForm is the subroutine that wipes all of the text boxes clean and clears out the labels. Next, there's a loop that runs 25 times. Each time it runs, it generates a new random number and stores it into double array 1. Then, double array 1 is copied into double array 2, and double array 1 is also copied into double array 3. This way, I have 3 random arrays that are all exactly the same. That way, when I compare the 3 sorting routines, it will be a fair comparison. Lastly, I call the PrintArray Subroutine. This will print an unsorted array to the first text box. The second button is an unoptimized bubble sort. This is directly from the notes from the PowerPoints at the beginning of the video. You have an outer loop that runs for all elements of the array, 0 to 24, an inner loop that runs 0 to 23, 1 less, an if statement to determine if we should swap the 2 values, and inside the if, a swap routine. The swap is just the subroutine that I wrote earlier. After the array is sorted, the array is then printed to the text box. The next button is an optimized bubble sort. The outer for loop has been replaced with a do while loop. When the while loop starts, sorted is assumed to be true. We assume it's sorted until proven wrong. And we can be proven wrong if a swap happens. So you'll notice that sorted starts at true, and inside the if statement it goes back to false. And as long as sorted is false, this will continue to run. To help you understand why this while loop helps, assume you have a 10-element array, but the 10-element array is already sorted. If you run it through an unoptimized bubble sort, the outer loop will run 10 times, and the inner loop will run 9 times. Therefore, the check will be made 90 times. Now, run that sorted array through the optimized bubble sort. The while loop assumes the array is already sorted. It runs through the array 1 time and realizes it is sorted and stops after 1 pass. Therefore, the comparison is only made 9 times. And 9 comparisons is a lot faster than 90. You'll also notice on the inner for loop, we're not going up to 23 anymore. We're going to a variable called int stop. Every time the inner loop runs, 1 value is pushed all the way to the bottom and is in the correct position. So if we have 25 values and the 25th value is in the correct position, we only have to check 24 values the next time. That will push the 24th value into the correct position, and therefore the next time we only have to run to the 23rd value, and so on. So every time we run the inner loop, its stopping condition goes down by 1. After this routine runs, we print the array to the text box. Version 2 of the optimized bubble sort is nearly identical to version 1. The only difference is, instead of just decrementing the stopping condition by 1, we record the location of the last swap. Assume you have a 25 element array, and the last 5 elements are already in the correct position. If you run through the routine, there's no reason to check the 25th, 24th, 23rd, 22nd, or 21st elements. If you record the fact that the last swap was made between 19 and 20, you then know you can stop at 19 and not worry about 20 through 25. Let's run this program and see what happens. When I press the Fill Array button, I get 25 random numbers. These 25 random numbers are now in 3 different arrays. The first array is going to be sorted with an unoptimized bubble sort. The second array is sorted with the optimized bubble sort version 1. And the third array is being sorted using the optimized bubble sort version 2. All 3 give the correct answer. So why would you want to use an optimized over an unoptimized bubble sort? Well, it has to do with how efficient the sorting routine is. An unoptimized bubble sort will always loop a fixed number of times. It doesn't matter if the array is sorted or not. It's always going to run the exact same number of times. The optimized bubble sorts monitor the array, and once they realize the array is sorted, they stop. I'm going to add a count variable to each one of the sort routines. This count variable will keep track of the number of times the comparison is made. It will then be printed on the labels underneath each of the text boxes. Let's run this program and see what happens. First, I'm going to fill the array. Next, I'm going to run the unoptimized bubble sort. The unoptimized bubble sort has sorted the array. However, it took 600 checks to sort this array. That's because the unoptimized bubble sort is essentially a brute force method. The outer loop will run 25 times because there are 25 elements. The inner loop will run 24 times, one less. 25 times 24 is 600. This subroutine will always make the same number of checks. Now let's run the optimized bubble sort version 1. This will also sort the array. However, this routine only took 285 checks. This advantage comes from the outer while loop, which stops once the array is sorted. The inner loop also has a decaying stop condition. It basically doesn't check as much each time it runs the routine. The optimized bubble sort version 2 will also sort the array, but it will take even fewer checks. This routine only took 250 checks, 35 less than version 1. In a worst case scenario, the number of checks that version 2 needs to make is the same as version 1. Let's run this program again. Fill the array, run the unoptimized bubble sort, which took 600 checks. Version 1 of the optimized routine also sorts and took 290 checks, and version 2, which also took 290 checks. Again, the worst case scenario for an optimized bubble sort version 2 is that it needs to make the same number of checks as optimized bubble sort version 1. Let's run this program again. Fill the array, 600, 234, 224. This video demonstrates that unoptimized bubble sorts are a lot slower than optimized bubble sorts. However, this speed comes at a cost. The code for an optimized bubble sort is a lot more complex than a simple unoptimized bubble sort. In review, this video covered 3 different sort routines: the unoptimized bubble sort, the optimized bubble sort version 1, and the optimized bubble sort version 2. There are many more sort routines than this, but these 3 are a good introduction to sorting an array. An unoptimized bubble sort is shown below. It is a simple sort routine to write and understand. However, it takes more execution time than necessary, and it becomes more and more inefficient as the array gets larger. Note, in this example, max is the last array element. The optimized bubble sort version 1 is shown below. It is much faster than the unoptimized bubble sort, but more complicated to write. Note, in this example, max is the last array element. The optimized bubble sort version 2 is shown below. It is a little faster than the optimized bubble sort version 1, but it is more complicated to write. Note, in this example, max is the last array element. If you find these videos useful, please like and subscribe. It is the only way I can continue to make these videos.